So who remembers what we're talking about? Diagonalization. Yes, exactly. Diagonalization. So 6.3 diagonalization. Right? And what have we done so far? What have we gotten so far? What have we done so far? Like, what kind of result do we have so far? Anybody remember? What did we get? We said something about getting eigenvectors, right? What was it? Under certain conditions, you have linearly independent eigenvectors, right? When do you have linearly independent eigenvectors? People are nodding, nobody's talking. Yes, yes. Right, so you have this theorem, right? You have a matrix. Right, and something happens, then you have linearly independent eigenvectors. Right? If you have a bunch of eigenvalues, if you have distinct eigenvalues, right, then these guys, if you have eigenvectors corresponding to those values, right? If eigenvectors corresponding to those values, then they're linearly independent, right? Then the VI are linearly independent, right? Right? Yeah. What? Something going on. Okay. These guys are linearly independent, right? And we had a corollary of that, which was that if your matrix, if A has n distinct eigenvalues, then we would have n linearly independent eigenvectors, right? And so we would have an eigenvector basis. Eigenvector basis of Rn. Okay? You'd be able to find, right? Because there would be n distinct eigenvalues, so that you could find n linearly independent eigenvectors. That would be your eigenvector basis, right? And last time, you recall that we said that if B is an eigenvector basis, with eigenvalues lambda 1 to lambda n, say, then the matrix representation, right, so then the matrix representation turns out to be diagonal, right? The matrix representation of A, or more properly we should say of T sub A, with respect to B and B on both sides, is diagonal. Right? It's diagonal with, it looks like lambda 1, lambda 2, lambda n. It's diagonal with the eigenvalues down the diagonal. Right? Okay, you remember that? Everybody remember that? Right? The way we saw it was that, right, phi, the new matrix has columns. Remember how you get the columns of the new matrix? Well, you take A times the ith basis element, right? A times the ith. You let the transformation act on the basis elements, right? And then you take the coordinate vector with respect to that basis, right? You take the coordinate vector with respect to that basis, right? This is the ith column. Ith column, right? But this is an eigenvalue, right? So when you an eigenvector, so when you hit it with the matrix, it just gets multiplied by a number, right? So the columns look like this, right? The coordinate vector of lambda I bi with respect to the b basis. But what's the coordinate vector of lambda I bi with respect to the b basis? It's just going to be how do you express lambda I bi as a linear combination of these guys?
Oh, just lambda.
It'll just be lambda I bi and 0 of everybody else, right? 0 b1 plus 0 b2 plus 0 bi plus 1 plus 0 bn, right? And so what's the coordinate vector? It's going to be 0, 0, 0, 0, 0, 0, lambda I 0, 0, 0, 0, 0, 0. So 0, 0, 0, lambda I 0, 0, 0, 0, 0, 0. Right? And so, right, so the first column is going to look like lambda 1, 0, 0, 0, 0, 0. The second column is going to look like 0, lambda 2, 0, 0, 0, 0. Right? And that's what we have here. Right? So that's why the matrix representation with respect to a basis of eigenvectors is diagonal. Okay? If you remember all that stuff we did before with the matrix representations. Okay? If you don't, there's actually a simple way of thinking about this. So in the book, they actually just pretend that you don't know this, and they give a different proof. So let's give that proof. Okay. So before we give it, let's introduce sort of an obvious definition. If you have an n by n matrix, if there exists an invertible matrix X such that X inverse AX is diagonal, then we say A is diagonalizable. Or some people say just diagonable. Okay. Diagonalizable, diagonable. One takes a little bit less work. Diagonalized by the matrix X. So we're going to say basically what we said here. We're just going to say it again and see that you can see it in a really simple way. Theorem: A is diagonalizable if and only if A has n linearly. So again, A is an mi matrix. I'm forgetting to say that. Just know that that's what it's going to be. If and only if A has linearly independent eigenvectors. In other words, Rn has an eigenvector basis. So, if you understood what we did before, then you should be like, yeah, of course, why are we saying this again? This is exactly what we set up there. Okay. But this is sort of maybe a simpler way of looking at it. So here's the proof. Say, okay, well, suppose there exists a basis of eigenvectors. V1 through Vn. Suppose you have these eigenvectors V1 through Vn. Okay. Let X be the matrix where these guys are the columns. V1, V2, through Vn. Okay, so use that basis, use those guys as the columns of your matrix. Okay. What is A times X? What happens when you multiply a matrix, a bunch of columns on the left by some matrix? What?
The dot product of the column, the row of the column.
What's the question?
The question is, what am I going to write here?
Another matrix.
Another matrix, yes. What will be the matrix?
The eigenvalues.
Well, not exactly. So when you multiply, if you got a matrix expressed as columns and you multiply on the left, then you've forgotten. You just multiply each column by the matrix. Okay, so this is something we noticed really early on, but maybe it was so long ago that people were forgotten.
Wait, why would you get the eigenvalues?
You will. So just right. So what happens then, right? You get AB1. Well, that's going to be lambda 1 B1 because each of these guys is an eigenvector. Lambda 2 B2, lambda n Bn. Okay. Now we're going to cleverly rewrite this last part as V1, V2 through Vn times the diagonal matrix lambda 1, lambda 2, lambda n. Okay. Again, using our rusty knowledge of matrix multiplication. Okay, but you see these are the same. You can multiply this, you're going to get this, right? And let's call this thing D for diagonal. And what you see is that AX equals XD, right? In other words, X inverse AX is this diagonal matrix. Okay. So whenever you have a basis of eigenvectors, then you can use that thing to create a matrix that you conjugate A by and get a diagonal matrix, right? In other words, you're similar to a diagonal matrix. You're diagonalizable. Okay? Everybody all right? Okay, and then the reverse direction, which is really the forward direction, basically you just reverse this whole thing. You say, well, look, suppose there exists an invertible X such that X inverse AX is diagonal. Right? Is some diagonal matrix D. Okay, right? In that case, AX equals XD, right? But that means that A times x1 through xn equals x1 through xn times d1 through dn. Right? But that means, of course, that a x1, a x2, a xn equals d1 x1 through d1 dn xn. Right? But then you've got, right, so then the xi, whoops, then the xi are eigenvectors. Right? And they were a basis because this guy is invertible, so they're an eigenvector basis. So having being diagonalizable is equivalent to having an eigenvector basis. Okay. Again, if you understood, well, what we were doing in chapter 4, then this is no surprise to you. But this is sort of an easier way of thinking about it. If you like this way, even if you don't remember what you did in chapter 4, you can still understand it. Back here, in the matrix representation way of thinking, right? We're going from Rn to Rn. We have the T sub A here. We use B to get your coordinate vector maps, right, to Rn here, right? And then we get this diagonal. We get this diagonal matrix. The matrix representation turns out to be this diagonal guy, right? This thing going backwards is x. This thing going forwards is x inverse, right? And so you get that x followed by a followed by x inverse equals d. Okay, so it's exactly the same thing, just different point of view. Okay. So anyway, the moral is a pretty simple one. Having a basis of eigenvectors, it allows you to diagonalize. Okay. So let me give you an exercise. Diagonalize a matrix. 5, 6, -2, -2. Okay. Take 2 minutes and see if you can follow the procedure that's on the board and, diagonalize a matrix. Okay, let's do it together. What do we need to do to diagonalize a matrix? What's the first thing?
Eigenvector.
Find the eigenvectors by, how do we get the eigenvectors? By looking at the determinant of a minus lambda I. Look at the characteristic polynomial to get the eigenvalues, and then we use the eigenvalues that they tell us what null spaces we need to look at to find the eigenvectors, to find the eigenspaces, and thus the eigenvectors, right? Okay, so you say, okay, we need to look at the characteristic polynomial, right? In other words, the determinant of 5 minus lambda 6, -2, -2 minus lambda, right? It turns out to be lambda minus 1, lambda minus 2, I hope, right? And then, so you need to factor, you need to multiply and then factor. And so you get that the eigenvalues are, right, eigenvalues are 1 and 2, right? And then we need an eigenvector basis. So let's find some eigenvectors. Right. So we look at the first, at eigenspace E sub 1, right, which is the null space, of, right, of A minus 1I, right? In other words, the null space of 4, 6, -2, -3, right? So you do your Gauss-Jordan reduction on it, right? And you end up with 2, 3, say, right? And so the null space turns out to be the span of the single vector -3, 2. Say. Okay. Right? And then E2, same thing, right? We look at this guy minus 2, right? So we get 3, 6, -2, -4. Same thing as 1, 2, 0, 0, right? And so this thing turns out to be the span of -2, 1. Okay, right? So we get an eigenvector basis, right? We can take these two vectors, -3, 2, and -2, 1, as an eigenvector basis, right? And we use them to diagonalize, right? So we let X be the matrix -3, 2, -2, 1, then X inverse AX turns out to be a diagonal matrix, right? What's the diagonal matrix?
1, 2.
Diagonal matrix with 1 and 2 down the diagonal, right? If we had taken the basis in the opposite order, then the eigenvalues would be in the opposite order, right? It would have been 2, 1. Yeah, Miranda.
I'm confused because like we already knew that 1 and 2 were the eigenvalues.
You confused that what?
Well, we already knew that 1 and 2 were the eigenvalues.
So why did we need to even
Yes.
diagonalize it?
Yeah.
Well, just because I wanted you to find the matrix that actually does the diagonalization.
But like, how would you find the matrix without finding the eigenvalues first?
You need to. You have to find the eigenvalues first.
Then why can't you just like write the eigenvalues diagonally instead of?
Well, you don't. So okay. So we lucked out in a certain sense because what happened was that we have. So in this case. So notice that, in fact, not all matrices are diagonalizable. Not all matrices are diagonalizable. So you might, we lucked out here because we got to this point and we said, oh look, we're in R2, and we've got two distinct eigenvalues. We're guaranteed an eigenvector basis. And so we know that its diagonal form, this thing is going to be diagonalizable, and we know what its form is going to be. Okay, but what happens if this were -1 squared? In that case, we would not know if we're diagonalizable or not, right? And what we'd have to do is look at see if we could, we'd have only one eigenvalue. We have to see if the null space is two-dimensional, right? If the null space is not two-dimensional, well, then you can't diagonalize. Okay. So maybe you get to this point and recklessly say, oh yeah, I've got two eigenvalues, so my matrix can be diagonalized like this, right? But actually that's false. That's unknown. Once you get to this point, you don't know. You have to calculate a little bit more and then see what happens. Okay. So yeah. So it's true that in this case it worked out for us, and you could have stopped at this point and said, I know what the matrix is going to look like. Yeah, Abel.
So do we only need to do this if we have repeated roots?
In order to figure out if it's diagonalizable or not, yes.
But if it's distinct roots, we can just do that. Like, we can just write it diagonally.
At this point you know that it will be diagonalizable, and that you can, if you got distinct roots, yeah, you know what it's going to look like. But you wouldn't know what matrix would do that for you, and maybe that's useful information to you. Okay, so this actually leads into the next idea, which is okay. So a bunch of definitions. First off, if A does not have an linearly independent eigenvectors, we call it defective. Right? So, in other words, if it's not diagonalizable, right? i.e., if A is not diagonalizable, then we call it defective. I should say that I don't think I've seen this term outside of this textbook. So maybe just some word that the author came up with. I doubt it. It's probably used somewhere, but I've never seen this term used. Okay. There are a couple of other definitions. To suppose that lambda naught, okay, and again, I always forget, right, that this is in my matrix, just remember it. Suppose lambda naught is an eigenvalue of A. Okay, in other words, a root of the characteristic polynomial. Root of the characteristic polynomial. So, definition A, we call the degree of lambda naught as a root the algebraic multiplicity of lambda naught. So for example, here, these are all just single roots, right? These are not double or triple roots. These are all single roots, right? So the algebraic multiplicity are 1 and 1, right? They each have algebraic multiplicity 1. Okay. Definition B, we call the dimension of the eigenspace, the geometric multiplicity. Okay, so again, going back to our example, right? The eigenspaces were all dimension 1, right? These guys, this was dimension 1, this guy was dimension 1. So the geometric multiplicity was of both of these eigenvalues was also 1, right? The algebraic multiplicity and the geometric multiplicities turned out to be the same. Okay, everybody getting the distinction? There's algebraic multiplicity, the degree of your root, as a root of the characteristic polynomial. There's a geometric, the dimension of the eigenspace. Okay, so we'll see in a second that the geometric multiplicity is always less than or equal to the algebraic multiplicity. The geometric multiplicity is always less than or equal to the algebraic multiplicity. Okay. Now notice the sums of the algebraic multiplicities of all the eigenvalues is what? The sums of the algebraic multiplicities of all the eigenvalues, well, that's going to be the sums of the degrees of all the roots of your polynomial, which is degree n. So all those degrees are going to add up to n, right? Is n. Right? If you have a quadratic, then it factors into the number of roots you have is equal to the degree of the polynomial. Okay. That's the fundamental theorem of algebra. You've probably never seen a proof of that because it requires probably the quickest way to see it would be to take a course in complex analysis. It's actually proven in a complex analysis course. Okay. But anyway, like the number of roots you have is equal to the degree of your polynomial. Okay, so this so the sums of the algebraic multiplicities is n. So coming back to where our setting here. Notice that the geometric multiplicities are all less than or equal to the algebraic, and the algebraics sum to n. Right? So the only way to have an eigenvector basis is if the geometric multiplicities equal the algebraic multiplicities for all eigenvalues. Right? Because if you're less than if one of them is less, then you're not going to get n linearly independent eigenvectors. Right? You can't get n linearly independent eigenvectors, right? Unless you've got enough of them. Right? Okay. So let me give an example. Right? And yeah, okay. Let me give an example. If we consider the matrix 2, 0, 0, 0, 4, 0, 1, 0, 2. Okay. If we look at the characteristic polynomial, you see immediately that it's 2 minus lambda squared, 4 minus lambda. 2 minus lambda squared, 4 minus lambda. And so the eigenvalues are called are 2 and 4. Okay. And you notice that the eigenvalue 2 has algebraic multiplicity 2. Right? 2 has algebraic multiplicity 2, 4 has algebraic multiplicity 1. Okay? But if we look at a minus 2I, well, that becomes 0, 0, 0, 0, 2, 0, 1, 0, 0. Okay. And so you see that, x1 is 0, x2 is 0, and x3 is anything. Okay. So this has a one-dimensional null space, right? Where x3 can be anything, but x1 and x2 have to be 0, right? So the geometric multiplicity is 1, even though the algebraic multiplicity is 2. Okay, so this is actually not diagonalizable, right? It's a defective matrix. So this matrix cannot be diagonalized. Okay, so let's explain that comment that the geometric multiplicity is always smaller than the algebraic multiplicities. So here, the geometric multiplicity is always less than or equal to the algebraic multiplicity. Okay, here we go. So let's say that lambda naught is an eigenvalue with geometric multiplicity d. Okay. Geometric multiplicity d, and okay. In that case, then we can find d linearly independent eigenvectors. Call them v1 through vd. We know that the eigenspace has d dimensions, so we can find d eigenvectors in that eigenspace, right? All with the eigenvalue lambda naught. Right? Okay, so now, but we don't have an eigenvector basis, right? We just have, these d eigenvectors. Okay. Extend the vi to a basis of Rn, right? That we saw ages ago that if you have some linearly independent vectors, you can throw in some more vectors and turn it into a basis. So we call that basis v1, vd, vd plus 1, to the n. Okay, but these guys over here are not necessarily eigenvectors. So we're not saying that we have an eigenvector basis, but we've got a basis, and the first d elements are eigenvectors. The matrix representation, so let's call this thing B. The matrix representation of A with respect to B and B looks like what? What can you say about the matrix representation, Ben?
It just has like the lambdas and diagonal.
So are you telling me that it's a diagonal matrix? This lambda knots down the diagonal like that? No, not exactly. Not exactly. Because we only have the first D, only the first D elements are eigenvectors. Ethan? Okay. Only the first D guys are eigenvectors. So this doesn't go all the way down. Right? It stops after D columns. Okay. So you have something like this. You got lambda naught down to here. So the first D columns look like this. And you've got 0 above and 0 below. Right? But then after that, you don't know. Right? There's some other stuff. Right? Right? Everybody okay? Right? Because, right, how do you get the first column? Remember, you look at how the transformation works on the first element, and then take the coordinate vector with respect to that. You're going to get, lambda 1, 0, 0, 0. The second one will be 0, lambda 2, 0, 0, 0, 0. Right? And then after when you get to d plus 1, you have no idea what happens, right? So after that, who knows what happens? But before that, things look simple. Okay. Okay. So then the characteristic, right? And so this is what we denoted as what do we call this? X inverse, right? Where these guys, X is the matrix with these guys as the columns. Okay. So then the characteristic polynomial.
Wasn't it like X inverse AX before? Did we switch it? Wasn't it X inverse AX?
Was it? I don't remember. So, yeah, I'm sorry. Okay. Yeah, I'm sorry. So yeah, X inverse AX. X. Okay. The characteristic polynomial of X inverse AX looks like what then? What happens when you take the characteristic polynomial of this thing? Well, you're going to have the determinant of this thing minus lambda, right? So you're going to have lambda naught minus lambda, lambda naught minus lambda, lambda naught minus lambda. So you're going to have lambda naught minus lambda to the d times some other stuff. Yeah.
What's the word before polynomial?
Characteristic. Right? So what does that tell you? So lambda naught has algebraic multiplicity. So let me take this one. The algebraic multiplicity of lambda naught is at least d. it might be more than D. Maybe it shows up, maybe there's some term over here that involves, lambda naught minus lambda. Okay, but at least it's D. Okay, but D, right, so it's greater than or equal to D, but D was, remember, the geometric multiplicity. Okay, I cheated you. Moran.
Oh, I don't think I know what the cheating is, but.
Yeah, you have a question?
Would it be possible for QX to have like a negative degree?
No, it's a polynomial, right? So it's going to be right. What you're going to get is the characteristic polynomial of this thing here, of this block here.
So are those numbers or no?
These are numbers, right? So these are, you've got some numbers, you've got a matrix here. You're going to get the characteristic polynomial of this part times the characteristic polynomial of this part. It's just another polynomial. So no, you're not going to get negative degrees. Okay. So now, we're actually not completely done here. The thing is that this is the algebraic multiplicity of lambda naught from the characteristic polynomial of x inverse ax. Right? This is the wrong matrix. Right? This is the wrong matrix. We got the algebraic multiplicity from the wrong matrix. But it's still okay. It's still okay. Just give me a second and I'll finish it up here. Okay. Are we in trouble? We're not in trouble. Because if we look at the characteristic polynomial of x inverse ax, you can rewrite this as the determinant of x inverse a minus lambda I x. Right? Because if you multiply these guys out, you're going to get x inverse a x minus x inverse lambda I x. But this is the identity matrix, and so you're just going to get lambda x inverse x, which is just lambda I. Okay. So this is the same thing. Okay. But you can use your understanding of the determinant and say, well, this is the determinant of this times the determinant of this times the determinant of this. And these things are reciprocal. The determinant of x and the determinant of x inverse are reciprocal, right? So you just end up with this thing equals this. Okay. So the characteristic polynomial of x inverse ax is the same thing as the characteristic polynomial of a. Right? So this is the same thing as the characteristic polynomial of a. Okay. So you say, well, look, like the algebraic multiplicity of lambda naught is at least d in this polynomial, but this is the same polynomial, right? So the algebraic multiplicity, we can actually say multiplicity of lambda naught with respect to a, not x inverse a x, is greater than or equal to d which is the geometric multiplicity. Okay, and that's what we're trying to show. Right? That the geometric multiplicity is always less than equal to the algebraic multiplicity. Any questions? I feel like people are a little bit confused. People get it? People get it? Okay. Okay. Okay, that's it for today. Have a nice break, everybody.